And we'll go. So I want you to remember and keep in mind what we learned in chapters 13 through 16 about addition of nucleophiles, nucleophilic addition to carbonyl compounds, and also nucleophilic acyl substitution reactions. We're going to put pause on those, but we're coming right back to them. In chapter 17, we're going to talk about a new class of nucleophiles. Focus in 13 through 16 was all on the electrophile, the carbonyl compound. In chapter 17, we're going to be dealing with enolates as nucleophiles. So we need to spend a little bit of time setting up what an enolate is and thinking about its reactivity. So an enolate is what you form as the conjugate base of a carbonyl compound. So here is just an average, ordinary, everyday ketone with a carbonyl carbon and an alpha carbon. And the alpha carbon's pKa is more acidic than you would expect for an sp3 hybridized carbon-hydrogen bond. The pKa for a proton alpha to a ketone is around 20, and that's in contrast to if the carbonyl wasn't there, then the pKa for that proton would have been around 50. So that's a 10 to the 30-fold increase in reactivity. And of course, the reason for that is resonance stabilization of the conjugate base. So this is something that you've probably known for a long time, but we're going to spend a little bit of time on today. If we draw the conjugate base of the carbonyl compound, we can show that the negative charge on the alpha carbon left behind after we deprotonate the alpha carbon is stabilized by resonance. We simply move the electrons on the alpha carbon over to form a pi bond with the carbonyl carbon, and then we break the carbon-oxygen pi bond and put the electrons out on the oxygen. And what we learn from this is that the purple electrons from the carbon-oxygen pi bond are actually delocalized not only on the not only in the space between carbon and oxygen, but also between the carbonyl carbon and the alpha carbon. Okay, so they actually spend their time in all two places. Similarly, we learned that the lone pair on the alpha carbon is also delocalized onto the carbonyl oxygen. And that's what resonance means. A couple of things. Resonance does not mean we are hopping back and forth between those two structures. It doesn't mean that the negative charge is at 1 minute on the alpha carbon and the next minute on the oxygen. It means it is simultaneously in both places. Partial negative charge on both the oxygen and on the alpha carbon. You can draw the enolate resonance structure, the enolate conjugate base, in either of those two ways, and either is okay. Your textbook will most often draw it like this, liking this one because it puts the negative charge on the most electronegative atom here, which is oxygen, and that's fine. I like to draw it this way because we will see that enolates as nucleophiles react almost always on the alpha carbon. Now, the reason for that is a little bit challenging to think about. If you think about the enolate as a nucleophile, the most reactive electrons in the enolate should be the ones that are delocalized on the alpha carbon and on the oxygen, the ones that are associated with the negative charge. But you might have to worry about, is that enolate going to react with its electrons on the oxygen or on the alpha carbon? And the answer is enolates are almost always reactive more on the alpha carbon than on the oxygen, which is a result you might not get to if you were solely thinking about electronegativity. If you were thinking only about electronegativity, you'd say, well, this is the more stable resonance structure, therefore the enolate should attack from the oxygen. And that actually ends up being the wrong answer. So we need to talk about why enolates are more reactive on the alpha carbon. And a complete picture of this requires a little bit of stuff with MO theory. So get ready. I know you like that. Sorry about the mic. If I bend my head down and then talk into it and breathe, it's going to make a loud sound. So I'll try not to breathe while leaning downward. How's that? Now I can't even lecture because I'm worried about breathing. Right, so you're used to the fact that this carbon-oxygen pi bond comes from what atomic orbital on oxygen and what atomic orbital on carbon? P, right? Used to pi bonds. What about this adjacent alpha carbon? What is its hybridization? Ah, good. I wanted you to say that. Some of you said sp2 and some of you said sp3. This is an important controversy we need to resolve. Those of you that said sp3 saying it because there's 4 groups around that carbon. One of them's a lone pair. What is the hybridization of the alpha carbon here? Because it's in a pi bond. Does resonance mean we're switching back and forth between tetrahedral and trigonal planar geometry? No, in fact, you cannot move atoms in resonance. Therefore, if it's sp2 hybridized here, alpha carbon must be sp2 hybridized there. Always, forever, no exceptions. Yes?
So if it's sp2 hybridized there and sp3 there, and it has to be sp2, isn't it also sp3 on the other side? Or does the sp2 have priority?
So, I'm sorry, which one?
So if it's sp3 with the electrons on the left.
What I'm telling you is it's not.
It's not.
It's
so
sp2 in both places.
It has to be sp2.
And the reason for that is if the alpha carbon is sp2 hybridized, then the lone pair would be in a p orbital. Then it can line up with the other 2 p orbitals on the carbonyl oxygen and the carbon to create an extended system of pi molecular orbitals that allow the lone pair to be delocalized. And that pays for that atom being sp2 hybridized. In other words, in order for this lone pair to be resonance stabilized, it has to be in a p orbital where it can line up with this pi bond. And I'll show you what I mean by extended system of pi orbitals. But if you can accept that each of these atoms, oxygen, carbonyl carbon, and alpha carbon, have a p orbital on them that can line up parallel to each other, then I'll show you what these orbitals look like. One of the combinations, and I'm just going to write down the atom positions here in blue, carbon, oxygen, alpha carbon. One of these combinations actually looks like this. You get it from we're just taking a side view of 3 p orbitals lining up together side by side with the same wave function sign. There would be a lobe above and below the plane of the atoms, and they line up all with the same wave function sign, so there's complete and continuous side-by-side overlap. From this sort of overhead view, what that would look like is a large continuous lobe of electron density above the plane of the sigma bonds, we'll color it orange, and then below the plane of the sigma bonds, we would have the second lobe, the pink lobe of electron density. What we mean by this is that electrons in this orbital would simultaneously stretch not only across the car space between carbon and oxygen, but also in the space between carbon and the alpha carbon. So that's an extended pi molecular orbital system. We call that pi 1 because it's the lowest energy combination that we can get. The process that I'm showing you is the outcome of mixing 3 p orbitals together to get 3 new pi molecular orbitals out. And this involves the maths of MO theory that we will not get into. But I'll show you the results and how they relate to what you know by resonance. The second combination you would get by bringing the second combination has a lobe on the carbonyl oxygen and on the alpha carbon, but not on the carbonyl carbon. In fact, there is a node on the carbonyl carbon. And this orbital would look like this. There's a change in wave function sign as you move from the oxygen to the alpha carbon. From our sort of overhead view, what this would look like would be a lobe on the oxygen and a lobe on the alpha carbon, and a node that is a place where electron density goes to 0 in between the 2 atoms, and the change in wave function sign. It will turn out, and you'll see with these pi-type molecular orbitals that we're going to come back to in our chapter on resonance in benzene rings, that the more nodes an orbital has, the higher in energy it is. So that is the pi 2 orbital. And then the third pi orbital we get simply by bringing the 3 p orbitals together side by side with opposite wave function sign in between them. And there will be nodes in between each of the atoms, and we'll switch wave function sign like this. And if you were to draw this on our overhead view of our molecule, it's going to look very similar. An oxygen here, a carbon here, the alpha carbon here, lobes on each of the atoms, but not continuous overlap between the two because you've got places where wave function goes through 0 in between each of the atoms. Okay? That's pi 1, pi 2, and pi 3. Understand these are not, each of these is one orbital made from the alphabet of atomic orbitals that you have available. You mix 3 atomic p orbitals together, you get 3 new pi molecular orbitals out. And each of these represents a place where a pair of electrons could be. Yeah?
So these are all occurring at the same time?
Yep, all at the same time. We can order them in energy based on the number of nodes. So you can see 0 vertical nodes, 1 vertical node, 2 vertical nodes. And then we can fill them up with the available electrons. Now, what electrons are involved in this system of pi orbitals? They're the electrons that are involved in resonance. So we're looking for conjugated pi bonds, and we're looking for adjacent lone pairs. In this case, how many electrons do we have that are in pi bonds or adjacent lone pairs? 4, right? The 2 in the carbon-oxygen pi bond, the 2 on the alpha carbon. So we'll fill up these orbitals with the available electrons, and we see that pi 1 and pi 2 are filled, and pi 3 is empty. Now, I've told you that enolates are nucleophiles, so we don't care about the empty orbitals for nucleophiles. We just care about the filled orbitals, and we care about which one is highest in energy. Notice what our MO picture says. The highest energy electrons, the HOMO of this enolate, is on oxygen and on the alpha carbon, but never on the carbonyl carbon, because there's a node on the carbonyl carbon. Now notice how that correlates with what resonance told us. The lone pair electrons are simultaneously on the alpha carbon and the oxygen, but never on the carbonyl carbon. Exact same picture. And in fact, I'm just going to highlight this lone pair as being pink. It's the pink lone pair in our drawing above. And you can see how the lowest energy electrons, the ones that are delocalized across all the oxygen, carbon, and the alpha carbon, are the ones highlighted here in purple, the ones that are a pi bond here between carbon and oxygen, and then a pi bond here between carbon and carbon. Those are the lowest energy electrons. Okay? Do you see the relationship between what resonance tells you and then what this MO picture is telling you? Questions about that? Yeah?
Could you, theoretically, put, using energy or heat or light and somehow promote electrons to the empty pi 3?
Yes, you could promote electrons to the empty pi 3.
Could you draw that? Is that possible? Or is it
What that would look like is probably something that would have 1 electron here, 1 electron there. So you'd expect it to have sort of radical-like character with sort of unpaired electron reactivity. Okay, good. Others? Yeah?
It's fun to look at orbitals. They might be a little rusty.
Join the club. Everybody feels that way.
But elaborate on the pi 3 orbitals because of the nodes.
Why is it empty? Simply because we've run out of electrons. There were 4 electrons participating in resonance, and we fill them up from the bottom, and then we stop when we run out of electrons. Yep. Yeah.
So there's going to be anti-bonding orbitals as well, right?
So the issue of bonding and anti-bonding orbitals we summarized when you mix 2 atomic orbitals together. There was a bonding orbital and an anti-bonding orbital. When you mix more than 2, the math doesn't change. You just have to get the same number of orbitals out that you put in. So if you mix 3, you got to get 3. We'll see in benzene if you mix 6, you got to get 6. And whether they're bonding or not will depend on the shape of the orbitals. And we'll walk through that only a little bit. For a hint, I will tell you that this lowest energy orbital is bonding. This one here is actually non-bonding. It's sort of a lone pair energy orbital. And this one here is anti-bonding. And I could show you how to go through and make that decision, but it's not important for now. Okay. Now, we started this discussion of the orbitals so we could answer the question, why is the enolate more reactive on the alpha carbon? We're going to answer that now. Do you remember back when we introduced the carbonyl functional group and I said the pi lower energy orbital, the pi bonding orbital leans toward the oxygen because it's more electronegative, whereas the pi star correspondingly leans toward the empty orbital, leans towards the carbon. We're going to see something similar here because oxygen's involved. So this pi 1 orbital we will see leans toward oxygen. The lower energy electrons lean towards the more electronegative atoms. So if we were to draw what this orbital actually looks like from the side, we would see that the orbital gets bigger on the oxygen than on the alpha carbon. It's just biased towards the oxygen. And that's the lower energy bonding electrons. Correspondingly, you can show that the highest energy electrons lean toward the alpha carbon. So if we were to draw sort of from the side what this looks like, here's the oxygen, here's the carbon, here's the alpha carbon. The orbital would be bigger on the alpha carbon than on the oxygen. And again, this is just my representation of it. You could do the math and show this. But because the HOMO leans towards the alpha carbon, therefore enolates are reactive, more reactive as nucleophiles on the alpha carbon. Okay. So with that, let's now talk about different kinds of enolates. We've dealt with a ketone so far. Let's deal with enolates of varying composition. Unless there's anything more we want to ask about this. Yeah?
In the I2, why does it lean towards the alpha carbon?
Why does it lean towards the alpha carbon? Short answer is the math that makes it that way. So I realize that's completely unsatisfying. That's another way of saying I don't really know. Qualitatively, you can think of it as if the oxygen's more electronegative, it's going to pull the lowest energy electrons toward it more tightly than the higher energy electrons. I think that's unsatisfying. I'm disappointed in my answer, but what are we going to do? Okay. So when we started this semester, we ranked carbonyl compounds in terms of reactivity. And the basic thing we were doing was saying carbonyl compounds are usually electrophiles, so the more electron poor the carbonyl carbon is, the more electrophilic it's going to be. And electron donating groups attached to the carbonyl carbon should make that carbon less electron poor and therefore make the carbonyl carbon less reactive. This was why we said that aldehydes were a little bit more reactive than ketones, and this is why we said that esters were less reactive than aldehydes. We're going to use that principle here as well. Starting with an aldehyde, I'm going to draw it a little bit different than I normally do. And so here's the carbonyl compound, and then we're going to write the pKa of the alpha proton, the proton on the alpha carbon. And we're going to consider pKa trends among those types of carbonyl compounds, but we are going to see that those pKa trends mirror what you already know about the electron poorness of the carbonyl carbon. So as we've already said, the pKa of an aldehyde, well, I've told you the pKa of a ketone, which was around 20. The pKa of an aldehyde is actually more acidic, lower than the pKa of a ketone. So here is a ketone. There is its alpha carbon, and the pKa is 20. Now, if you draw the conjugate base of one of these carbonyl compounds, the conjugate base of one of these carbonyl compounds, you get the enolate. And you can see that the enolate is resonance stabilized, and we frequently draw, as I've done above, this resonance structure where there's a pi bond between the alpha carbon and the carbonyl carbon and a negative charge on the oxygen. But an alternative resonance structure that can help you understand what's going on here is this one, where we put a positive charge on the carbonyl carbon, negative charge on the carbonyl oxygen, and then a negative charge on the alpha carbon. You're going to look at that and say, that is a cruddy resonance structure. Why don't you have a pi bond when you could? And I agree with you, but it does illustrate an important point. The thing that makes the enolate stabilizable by resonance is the fact that adjacent to the alpha carbon, you have an electron poor carbonyl carbon. I've drawn with a resonance arrow, I've drawn with a red arrow what happens when those lone pairs on that alpha carbon can form a pi bond with the adjacent carbon. These are all resonance structures of the same thing, but the key point is an electron poor carbonyl carbon better stabilizes the negatively charged alpha carbon. On a more stable conjugate base should be a stronger acid, right? So with that in mind, why is the ketone less acidic than the aldehyde? Go ahead. Hyperconjugation of what?
Of the, what do you call it, the other alpha carbon, and the hydrogen and the oxygen.
Okay, yeah, you've got this adjacent alkyl group, which you have been told is an electron donor via hyperconjugation. Specifically, what we're talking about there is the adjacent carbon hydrogen sigma bonding orbital delocalizing a little bit into the carbon oxygen pi star. That makes the carbonyl carbon less electron poor, and a less electron poor carbonyl carbon is worse at stabilizing the negative charge in the enolate. In other words, the ketone enolate is not as stable as the aldehyde enolate. Okay, so we're not learning something new here, we're just applying knowledge we already have in a new context. A more electrophilic carbonyl compound should have a more reactive alpha proton, a more acidic alpha proton. Okay? Because the thing that makes the alpha proton acidic in the first place is the electron poorness of the carbonyl carbon. So we said before that esters were less reactive than ketones or aldehydes because of the donating OR group on the ester. We can draw an ester for you here. There, it's full-on resonance of the lone pair on the oxygen with the carbonyl carbon. What do you predict for the ester? More or less acidic than the ketone? Should be less, and in fact, you're right, it's 100,000 times less acidic. pKa is around 25. These aren't numbers for you to memorize, but they are trends for you to know. It's not important that the pKa of an ester is 25. It is important that the pKa of an ester is higher than that of a ketone, but you should already be able to figure that out based on what we've talked about. And you could use similar reasoning to predict, okay, the amide, which has an even better donating group than the ester, should have alpha protons with pKa's that are even higher or less acidic than that of the ester, and indeed that's true. And in fact, we won't make enolates out of amides. The pKa's are generally too high to be useful. Okay. All right. So let's now talk about how we can make alpha carbons even more acidic. In each of the examples we've dealt with so far, the alpha carbon has been adjacent to one and only one carbonyl compound, carbonyl carbon. What we're going to introduce now is a class of carbonyls called beta dicarbonyl compounds. And these are going to have alpha carbons that are adjacent to two carbonyls. So for example, take this ketone with an alpha proton here. And actually it has more than one kind of alpha proton, right? It's got, we could use orange here for this alpha proton, and we could use purple for these other alpha protons. Turns out the purple alpha protons have pKa's that are around 20, what you would expect for being adjacent to one carbonyl compound. However, the protons that are adjacent to 2 have a pKa of 9. So that's 10 to the 11, 100 billion times more acidic. And the reason for that is if you look at the conjugate base, we'll draw the conjugate base if we remove the purple alpha proton. You get this enolate, and that enolate can be delocalized onto either of the carbonyl oxygens. So you can draw this resonance structure, and that works. Or you can draw this resonance structure where the pi bond goes in the other direction. And you can see that the lone pairs on the alpha, whoops, that's kind of unfortunate color, isn't it? I'm going to just change it from orange. There we go, much better. You can see that the lone pair can be in 3 places instead of just 2 for a regular enolate. And increased delocalization makes the conjugate base more stable. And that's why the most acidic protons are these ones. Why do we call it a beta dicarbonyl compound? Because you have the carbonyl carbon, the alpha carbon, and then another carbonyl on the beta carbon. Those 2 carbonyls are beta to each other. And the fact that that pKa is 9, I mean, we shouldn't pass over that too quickly. That means it's more acidic than an alcohol. It's more acidic than water. It's even maybe more acidic than most ammonium ions. So you could completely 100% deprotonate that with hydroxide. And we'll take advantage of molecules like this in the future to do chemistry. And you'll see that often with these types of molecules, if we want to generate an enolate, we don't have to use a very strong base to do it. We can use a decently mild base to remove that proton, and it works fine. Now, you can mix and match types of carbonyls in beta dicarbonyl compounds and generate pKa's that make sense. For example, tell me what you predict if I replace one of the 2 carbonyls in this beta dicarbonyl compound with an ester. What do you predict for that alpha proton? Should it be more or less acidic than the beta diketone? Less. Why? Because esters are less electron poor because of the donating group, meaning the conjugate base enolate is going to be less stabilized. And indeed that's true. The pKa of this beta keto ester is 13, so that's 100, nope, sorry, it's 11, about 100 times less acidic. And then if I went to 2 esters, you'd predict that it would be even less acidic. And it is, almost in an additive way. That pKa is around 13. So you can mix and match and rank carbonyl compounds in reactivity simply based on, you can mix and match alpha protons in reactivity simply based on how electron poor the carbonyls are. All right, questions about that? Yeah?
Oxygen's acted as withdrawing groups,
Oxygens are electronegative. And when they're involved in pi bonds, they can, what you're talking about is something like this. But when they're adjacent to pi bonds, they can function as donating groups. The reason for that is lone pairs on that oxygen can do this. And that makes because they're sharing electrons with the carbonyl carbon, that makes the carbonyl carbon less electron poor. Yep. All right, others? Yeah.
What if you stuck a chlorine on there instead of an ester?
Chlorine where? On the alpha carbon instead of an ester? Yeah, you would predict, and maybe this comes up a little bit later in the chapter, though we may not talk about it in a lot of detail. Yeah, you would predict something like that would make the proton more acidic. Probably that's an inductive withdrawer, not a resonance withdrawer, so the effect may not be as big. There's another thing that's going to show up in your study guide that's going to be surprising to you, and that is that, hopefully not too surprising to you, that is that nitriles are basically like carbonyls. So protons that are alpha to nitriles can be acidic too, and you can make enolates for them. And you would predict that a proton that was alpha to a carbonyl and a nitrile would be relatively acidic. I don't actually know what that pKa is because I didn't write it down in my notes, but we'll just write acidic by it and hope for the best. Okay, so your text will do that occasionally. You're going to see the nitrile, like what's going on there. Just remember, treating the nitrile like it's a carbonyl, like it can stabilize negative charges by resonance, because it can. All right. So now we're going to talk about how to make the enolate nucleophile. There's two main strategies, and we're talking about two main strategies because in some contexts they're going to have different outcomes. So the first strategy is to make the enolate under reversible, and by that we mean equilibrating conditions, equilibrating or reversible enolate formation. What we mean by that is we're going to use a base that's not strong enough to 100% deprotonate the alpha carbon. So as an example of this, let's go with our boring ketone whose pKa is around 20, and we'll use as a base hydroxide. And we'll just set this up as though it's chapter 2 of 351. We'll draw the conjugate base of our acid, and we'll draw the conjugate acid of our base. We'll write down this pKa, which is 16. Strongest acid loses its protons, so which side dominates at equilibrium? That makes sense? Everybody agree on that? So what this tells you is if you add hydroxide to this ketone, you've got, by a factor of about 10,000, maybe 99.99%, greater than 99.99%, and less than 0.01% of enolate. Okay, so that means that when you do form an enolate, most of the time it goes back to starting material. Why would you want to do that? Why would you ever want to do that? Well, it turns out 0.01% of a mole of molecules is still a whole lot of molecules, and that's enough often to get chemistry going. The other reason you'd want to do that is because hydroxide's a pretty cheap base. Third reason is you could use a protic solvent. You're not worried about the enolate getting protonated by the solvent again, because that's happening all the time anyway. It gets protonated by your base. And then the final reason is we're going to see that it matters. If we use equilibrating conditions, sometimes the nucleophile that we get, the enolate nucleophile that we get, is different than if we don't use equilibrating conditions. Let me give you an example of that. So first, answer this question. Which is higher or lower in energy? Which is higher in energy, starting materials or products? Products. That's why we have such a small amount of products. So it's uphill to get to the enolate. Okay, good. Now let's imagine a ketone starting material that we're going to modify just a little bit by putting a methyl group on one of the alpha carbons. Suddenly that gives us two different alpha carbons. I'm only drawing one of the alpha protons on each of these alpha carbons, the purple alpha carbon and the orange alpha carbon. Now, if we remove the proton from the purple alpha carbon, we're going to get the purple enolate, which we can draw like this. Or we can use the other alternative resonance structure, which would look like this. And then if we remove the orange alpha proton, we get to the orange enolate, which we could draw either with the negative charge on the orange alpha carbon, or we could draw the resonance structure that would look like this. Okay, do you see that those are both the enolates that would form. Do you see how they're different? One negative charge is on the purple alpha carbon, and one, the negative charge is on the orange alpha carbon. Those two enolates are actually called isomers of each other. They are constitutional isomers or regioisomers. So this reaction gave us regioisomeric enolates. And we want to know whether we're going to, when we prepare an enolate from this starting material, whether we just get a mixture of the two or whether we get more of one than the other. Go ahead.
I think you're going to answer what I was
Okay, good. So understand that if we make this page sort of an energy diagram, we're going to have the starting material down here, and we're going to have the enolates higher in energy. Now our question is, is there any difference in the stability of those two enolates? So let's look at their structures and then consider anything you might know or remember, possibly from 351, about that would help you decide which enolate is more stable. Go ahead.
Yeah, I think the purple one's more stable.
Okay, go ahead. Why?
Because it's because it's connected to a carbon, an oxygen, and a carbon, so it's got three kind of like stabilizing it.
Okay, so you like the purple enolate because the alkene here has two alkyl groups on it, whereas the alkene here only has one. Right, that's a principle from 351, right? You learned that more substituted alkenes are more stable. Remember that? I think that was in the chapter 7 or 8 on elimination reactions. Okay, yeah?
Is that because of the inductive effect?
So why is it that so that's a result from 351. Let's talk about that. You learned that more substituted alkenes are more stable. And that wasn't explained in a lot of detail for you in the text. One potential explanation is that alkyl groups are inductive electron donors, but why would that stabilize the double bond? It's not necessarily a very satisfying answer. And what's probably going on is the same kind of hyperconjugation as we saw with carbonyl compounds. We've seen that pi bonds adjacent to carbon oxygens hyperconjugate into the pi star, and that allows the carbon hydrogen sigma bond electrons to spread out. Probably that's occurring here. Adjacent CH bonds adjacent to the pi star of the alkene are donating electron density into the pi star. That spreads out the CH electrons a little bit and allows them to move lower in energy. So the reason more substituted alkenes are more stable is probably also because of hyperconjugation. But you can use that as a memorized result from 351. Yes, in purple you have the more substituted enolate, and that is more stable. In orange, correspondingly, you have the less substituted enolate, and it is less stable. Now, because we're not being particularly quantitative, I'm going to put the line for where the more substituted enolate is here, the line for where the less substituted enolate is here, and then I'm going to drag that down a little bit. Okay? And what we mean when you put hydroxide in with this starting material is that it's uphill to go to the purple enolate, but it's even more uphill to go to the orange enolate. Meaning that at equilibrium, which is the major enolate? Which do I have more of? Purple, right? I have more of this more stable enolate. So this is going to be my major enolate nucleophile when I'm using equilibrating conditions. And the products, we haven't even talked about what those reactions we're going to do later on are. They will involve introducing electrophiles and going downhill to something else, but the products will come predominantly through this major enolate. Notice that if we used an electrophile on the purple enolate, that electrophile is going to go on this purple alpha carbon, whereas over here it would go on the orange alpha carbon. That's a major difference, right? The new bond is made in a different place. And we call reactions that have different regioisomeric outcomes but prefer one over the other, we call them regioselective. So what I've just showed you is how to do regioselective enolate formation under equilibrating conditions. Your text will use slightly different language talking about this. Your text will call the more substituted, more stable enolate the thermodynamic enolate, by which they mean it's more stable. And you form it under reversible or equilibrating conditions. All right, second way to form an enolate is, as you might imagine, under irreversible conditions. So let's give you some examples of this. One way to do irreversible enolate formation is simply to choose, and you've already seen this one, choose a carbonyl compound that has an especially acidic alpha proton. So if I use this beta diketone where the pKa of the proton between two ketones is around 9, and then I use OH minus, and the pKa of this proton is around 20, it turns out the most acidic proton wins, and I make 100% of the desired enolate. And the reason I make 100% of the desired orange enolate is because that was the most acidic proton, and if I compare the pKa of the alpha proton to the pKa of the conjugate acid of my base, you can see that products are preferred here by a factor of like 10 to the 7. So one way to do this irreversibly is just use an especially acidic alpha proton. Go ahead.
So why would you not just do irreversible conditions all the time?
Yeah, why would you just not do irreversible conditions all the time when it works so well? If I wanted to use the more substituted enolate, you're going to see that under irreversible conditions, sterics actually matter more, and so you would get only the less substituted enolate. We're going there in just a couple of minutes. Okay? All right, another option, if you don't want to use a beta dicarbonyl compound, is to use just a regular alpha proton, but use a much stronger base. So this is a new base introduced to you. This is called, the counter ion is lithium. This is called LDA for lithium diisopropyl amide. Its conjugate acid has a pKa that's even a little bit higher than expected, probably because of the alkyl groups, has a pKa of 40, whereas the alpha proton alpha to a ketone has a pKa of 20. So by a factor of 10 to the 20, you can make 100% of this enolate. Now LDA is expensive and you can't use protic solvents with it. So if you wanted to save money and use protic solvents, perhaps you'd want to choose the other method that we talked about, the reversible enolate formation versus using LDA. But the real advantage of using LDA comes when you go back to the example we did previously, looking at the carbonyl compound that had a less substituted alpha carbon and a more substituted alpha carbon. And understand that with LDA, removal of the alpha proton is irreversible. You do it and then it's done. For reactions that are irreversible, the only thing that matters is not which product is more stable, but which one forms faster. For reactions that are irreversible, the only thing that matters is which product forms faster, and the faster product wins. It turns out that the less substituted alpha carbon is less sterically hindered. LDA is pretty bulky as a base. It's got those isopropyl groups, not quite as bad as a T-butyl group. But because of that, it has a hard time getting in close to the alpha carbon, so it will preferentially and regioselectively form the less substituted enolate because it's easier and faster. Faster to remove the orange alpha proton. And so for LDA, you can hope for 100% of the less substituted enolate. Well, we'll just say that the major enolate because selectivity is often not 100%, but the major enolate is the less substituted one. So this is the other reason why you'd want to use why you'd want to, depending on what enolate you'd want, you'll choose your conditions. If you want the less substituted enolate, you'll use LDA. If you want the more substituted enolate, you'll use the reversible conditions. Okay, questions? Yeah?
I think I missed that. Why does the LDA prefer the less substituted one?
The less substituted one is less sterically hindered, and LDA is a bulky base. And again, because it's irreversible, whichever one it prefers, it's stuck there. You can't go back and get the more substituted enolates. Okay, others? Yeah. Sorry. Yeah.
What exactly makes the reaction irreversible? Is it something about LDA?
The thing that makes the reaction irreversible, good question, is the huge difference in pKa's on either side of the equation. So 20 for the ketone and 40 for the conjugate acid of LDA. That means this reaction's downhill by a factor of 10 to the 20, which means once you're here, there's no going back. If you could go back, there would be plenty of time to, even if the less substituted enolate formed faster, if you can go back, on average, you're going to form the more substituted enolate as the major one. Yeah.
That's what I was saying.
Okay. All right. I think you guys have a test today, so we'll just be done. Good luck. May the force be with you.